All right. Welcome back, everybody. We are still in BGP, obviously. What we're going to be talking about in this lesson is similar to what we talked about in one of our previous lessons, which is the BGP path selection process. All right. We call this the BGP path selection algorithm or BGP path selection process. I decided to go ahead and do this lesson again for a couple of reasons. Number one, a few people didn't have a chance to participate in the first lesson. The recording is in the Google Drive, and you guys can take a look at that. I think it's saved as lesson number 60. But at the same time, I wanted to kind of add a little bit to what we were talking about in this particular case, because there are some additional caveats that we're going to take a look at. We're not going to be doing a lot of configuration in this particular lesson because we're going to focus on configuring and manipulating the path selection process over the next few lessons that we're going to be doing starting on Monday. All right, we'll give you guys a weekend to kind of catch up since we did our 3 lessons this week. So you guys will have the Labor Day weekend to relax and catch up if you need to catch up. All right. So that's what we're going to be talking about. I'm going to be referencing the notes that are saved in the Google Drive as well, called BGP attributes. I might actually be adding to this list here, but that's what we're going to be focusing on. All right. Really, it's what we call the BGP best selection process, best path selection process, I should say. We're going to talk about specifically how the order works, what is the selection process. We'll take a look at what are the different ways that we can manipulate the best path selection process. And then in later sections, we'll look at specific examples. We're not going to do that in this particular lesson, but in later lessons, we will take a look at specific examples about how we can manipulate these different attributes differently with things like local preference versus wait versus AS path versus MED and so on. Those will actually be the 4 primary attributes that we talk about in this lesson, and then we'll get into some of the tiebreakers and some of the other unique elements of the path selection process later on. This is a really, really critical point, and the primary reason is the document that we would normally reference for this particular process is not going to be available to you on the lab exam. So I do highly suggest that you become somewhat aware of how this process works. There's nothing you can do in the command line that's going to allow you to be able to infer from maybe a context-sensitive help or some other method as to how the selection process actually works. You could certainly take a look, by manipulating certain aspects and so on, but ultimately we need to be able to understand what this process is. The best path selection process controls which routes go into the routing table from the BGP table, and ultimately what we can then advertise to different peers in the topology. The process itself is actually standardized in RFC 4271. So if you want to see the actual standard component, it's actually in section 9.1, which is the BGP decision process section. So if I scroll down here and I go over to the BGP decision process section, we can see it right here. And in this section, we talk about essentially what we've already talked about once, and then what we're going to continue to talk about in this section here. So I do recommend that you take a look at this. This is more of an open standard view, if you will, of the BGP path selection process. You can also do a quick Google search for the BGP best path algorithm. And the first thing that should pop up here is Cisco's documentation on how they select the specific best path. There are some slight differences. Wait, for example, is one of those components that's included. And this would be a good document to go through. Basically, this is essentially the document that we went through when we did our initial discussion of the best path selection algorithm. But this document describes it from Cisco's point of view. So these are important concepts to understand. It's very, very important that you are familiar with this because, like I said, you're not going to have any reference documentation on the lab exam for this particular process. And they do love to ask about this on the written exam. All right. All right. Before we even consider going through this process of calculating different BGP attributes and going through the best path selection process, and I'm going to add this to this section here, there are some prerequisites that we need to consider in this selection process. All right. Number one, and this is first and foremost, we must have a route to the next hop. All right, we've talked about this many different times. BGP is a reachability protocol, which means when BGP presents prefixes, it presents the length, it presents the next hop, but it's really up to the IGP protocol to decide how to route to that next hop. We've said this many different times. If we don't have a route to the next hop in the routing table, in the RIB, the global RIB, then that's going to prevent our route recursion. We'll get a route recursion failure, and we won't be able to resolve to the destination, and the route ultimately would not be usable. If that route recursion process fails, we skip the whole decision process altogether. We don't install the route in the routing table. What you're looking for specifically, if I was to just go to one of my routers here and do a show IP BGP, what I'm looking for specifically here is the greater than symbol. That greater than symbol indicates that we do have reachability to the next hop, and we've selected a best route. You can see here best is identified. We've selected a best route, and we've been able to go through the recursion process to be able to identify our route. All right. This means that it is the best path. It can be installed into the BGP table, then it can be installed into the routing table, and ultimately it's the route that we would advertise to our peers. Now there is another component called this BGP synchronization. Now we haven't actually talked about BGP synchronization up to this point, primarily because it's really not something that we see too much. It's more of what we call a legacy rule. So we're not going to spend a whole lot of time talking about it because there's really no practical use case for it anymore. In fact, BGP synchronization used to be turned on by default. Now it's turned off by default. But originally we had routers in the core of our network, in the core of our autonomous system, that couldn't run BGP because they didn't have enough resources, they didn't have enough CPU or memory. So the solution was to redistribute BGP into the IGP protocol at the edge of the network. And we would basically synchronize the BGP information with the IGP routing table. So the rule said for every iBGP route, you would have to have a matching or corresponding IGP route, but in newer codes, this is generally off by default, okay? So let me just make a note here. Typically on the edge routers in the AS, and this required that all iBGP routes had a matching IGP route in the RIB in order for it to be even considered a possible path. And again, we're still talking about going through the process of path selection and being able to identify whether a path, whether a route is even eligible to go through the BGP path selection process. All right. Another general rule, and this is number 3 in this case, is that the AS path could not contain my own AS. All right, now if you think about that, what we refer to as the local AS. Now if you think about the logic here, it kind of makes sense. This is kind of a normal eBGP loop prevention technique. You can actually disable this. Well, let's just call this eBGP loop prevention technique. And you can actually disable this with, you'll see this with a lot of these individual options with BGP. You can disable this with the allow AS in. But the idea here is that, or you could do like something like an MPLS layer 3 VPN override, AS override. All right. So anytime I would see my own AS in the path, BGP would end up throwing away that particular prefix. So normally you would check the first ASN in the path to make sure that it's a neighbor. All right. But what about this idea that we don't want to include the local AS? Because ideally, if I'm receiving a route or a prefix from an external peer, and it includes my local AS, we know the route has to be originating from some sort of external resource because it has external AS information included. Otherwise, we wouldn't see any AS path information at all. So I would rather use my IGP process or my internal routing process to route to the closest external peer that lets me get out of the autonomous system. And I'm going to end up ultimately trusting the external route before I trust anything that, that looks as though it came from external, but it also includes my own autonomous system path. All right. The other component, and this depends on the operating system itself or the version of the code, is normally we would check to see if the first ASN should be my directly connected peers, right? Now think about that from that perspective, right? If we're talking about external routes that we're making routing decisions on. Keep in mind when it comes to BGP, we don't typically use iBGP to route internally. So a lot of these principles of best path selection have to do with external routing. It's not to say that the best path selection process can't be used to decide how to route internally, but primarily it's used to identify how we route externally. Okay. So obviously I'd want to make sure that the first ASN that shows up from prefixes that are advertised from external peers would be the peer that I'm directly connected to. That means that the information is trustworthy and we're not suffering from some sort of injection attack where somebody has spoofed the BGP session, the TCP session, excuse me, and they're injecting false information into the BGP process. So this is more of a security mechanism, and it's to protect against primarily route injection attacks. All right. All right. Now we could either disable this or enable this. There's a command that we actually use. I'll just reference the command here in case you guys want to see it a little bit later on. It's BGP Enforce. I can't remember if there's a dash or not. Enforce first. Let me check real quick. Config T router BGP 100 BGP Enforce. Yeah. Okay. So it's got the two dashes there. Just wanted to make sure that I had it correct in the syntax. So that's what's going to say where we're going to say, look, we're not going to accept routes. And I'm curious, let me see real quick since I'm here, do show run pipe section BGP. You can usually tell if this is a default or non-default configuration based on how it shows up in the running config. And we can see here it doesn't show up, right? So that's an indication that this is a feature that would be enabled by default. If I did a no BGP enforce do show run pipe section BGP, we would see that listed as part of the configuration, which means that's the non-default configuration. All right, that's another quick way, by the way, of being able to identify whether or not a specific configuration is part of the default, if it's enabled by default or not, is to see if it shows up in the running config. All right, so normally we would have that BGP enforce first AS command in there. You just wouldn't see it because it's part of the default configuration. Really all that this is an application layer check. And the idea obviously is that we want to see let me see, more to protect. We want to see our peers AS listed first in the AS path attribute, okay? And that's to indicate that we're actually getting routes from the actual peers rather than somebody injecting stuff that's not supposed to be there, okay? Now, those are the prerequisites. Once we've met all of those different prerequisites, then we go into the BGP path selection process, all right? I'm going to use this as a reference as I'm talking about this, just to kind of reinforce or reiterate what we talked about previously, but I'm going to add some additional things to this as well as part of our discussion. So the first thing is the weight, right? This is a Cisco proprietary attribute. We prefer the highest weight. It's a Cisco defined attribute. It's assigned locally by the router. It's not propagated to other peers. It can have a value from 0 to 65,535. There's a default weight applied of 32,768 for all paths that I originate, that I self-originate, and we have a default weight of 0 for all other prefixes. The higher the number, the more preferred this is, all right? And we can actually specify the weight based on a prefix. We can do this with route maps as well by just applying the weight value to our neighbor relationship or by using a route map and then setting the weight for prefixes that we're learning through that particular peer based on a route map applied to the neighbor relationship. The key here, all right, is this is a non-transitive local attribute, all right? That means that we're going to apply this policy inbound. That's one of the things that I didn't focus on the last time, but I really want to focus on this time is when you're applying policies, they need to be applied based on how you want to influence the route. Outbound policies affect inbound flow, and inbound policies affect outbound flow. So this is an inbound policy, which means it's going to affect how this router makes a decision on how to leave the network. So let's take a look at our topology real quick. And let me grab a snippet of this. And so I can just kind of reference a few things here. So let's say in this case, there's only really one place that I could apply weight in this topology, and that would be on router 5, right? Because router 5 has multiple choices on how to route out of the domain. So let's say it's for this prefix here, 7777. We're advertising that prefix in both directions. I'm learning that prefix on router 5 in both directions, and we'll see the syntax for this a little bit later on. But I want to influence how router 5 decides to leave the network, okay? So I could set a weight of 100 for this link. I could set a weight of 200 for this link for all the prefixes coming from R7, and I would end up preferring to use this link to route to the prefixes originated by R7 as opposed to the backup link. All right, it's a very, very simple attribute, very easy to manipulate, but again, it only influences how this one router decides to leave. And that's actually a good point, because the problem with this is that router 5 is the only one that's going to look at this attribute to make a decision, because router 5 is not going to send this attribute over to router 4. It's not propagated throughout the rest of the autonomous system, which means that only router 5 is making the decision locally. It's a locally significant attribute. All right? It's also why it's not really used that often. And that's because it changes potentially how one router might view the topology versus other routers in the domain. Okay? Other vendors, this is a Cisco proprietary attribute. Other vendors do have something similar, but in most cases you don't want to use this. You would rather use something that's more standardized, which is like local preference. So, all right, let's talk about local preference. This is defined as a well-known discretionary attribute, which means that it's a standard attribute, but we can choose to ignore it or we can choose to accept it, okay? The key to this particular attribute is that it propagates throughout the entire autonomous system, all right? the default preference value is 100. The higher the number, the better. We set this with BGP default local preference and then set the value. We can manipulate this as well if we wanted to. Maybe perhaps do this with a route map as well. All right. The other key thing I want to add here is this is not advertised to eBGP peers, only iBGP peers. Okay. The other thing is that it is carried through Confederation, eBGP. All right. Now, we didn't get a chance to really talk about that much. It's not really that critical in this case. But there is a trick with community signaling. There's a community signaling method to send certain community attributes to an eBGP peer in order for them to affect local preference. We look at this primarily from a scaling point of view, where maybe we're working with a particular provider. They don't want to manage a specific set of attributes. They want you to still be able to control the routing. So they're going to say, here's a set of community attributes that you can send me, which will then instruct me on how to control the decision process. And local preference could be one of those. So I could change the local preference of the route as it comes inbound. Again, this is an inbound policy which affects outbound flow, which will change my selecting, change how I select a particular path outbound. Remember, and I can't say this enough because it's really, really critical, inbound policy changes affect outbound traffic flow. Outbound policy changes affect inbound traffic flow. So this is, I should actually kind of identify that uniquely with each of these. This is an inbound policy. And this is also an inbound policy. All right. By the way, this document is saved in the BGP, kind of the BGP overview folder. So if you want to grab a new copy of this, you're more than welcome to. All right. So any inbound policy is going to affect outbound traffic flows. Weight and local preference, those are two of them that get set inbound to affect my outbound flows. All right. Locally originated routes. Well, we'll talk about that in a second. Let's go back to our topology diagram, and we'll get into step number 3 in a second here. But so now let's take a look at local preference. Now, local preference can because it is a value that gets propagated throughout the entire autonomous system, we could set a local preference, say on router 3, for routes that are coming from router 7. We could set a local preference on router 5 for routes that are coming from router 7, actually on both links. That information is going to get propagated to the rest of the domain, and then these routers will then make decisions based on those local preference values that are getting propagated within the autonomous system. In our particular case, it would only be router 4 making the decision, because router 4 is configured as a route reflector client. And this is the same topology that we'll be using in some of our actual use case scenarios that we're going to go through in some of the future lessons. All right, so this is very different than weight, because weight can only decide my egress point based on links that are connected to a single router, whereas local preference can affect my overall egress point based on multiple links that are connected to different routers within the autonomous system. We could still use local preference, for example, between router 5 and router 3, and then we could also apply weight on top of that on router 5. So we could say, okay, router 3 is going to have a local preference, and if you look again at the notes here, the higher the number, the better, right? Oops, sorry, right here, higher number is better. So let's say, for example, in our topology, router 3 is sending in a local preference of 100, and router 5 is sending in a local preference of 200. We could still use weight to select the path that we want to select outside of R5. So these local preference values are influencing how everybody routes in the autonomous system But once the traffic reaches router 5, then we can use wait to influence how traffic is going to leave router 5 and go to autonomous system number 51. All right? We can always control how data leaves our network. We can only suggest how data should come into our network. And, you know, we'll talk more about that a little bit later on, but we can offer suggestions to router 7 to say, hey, you're going to come in this way, or you're going to come in that way, but ultimately it's going to be router 7's decision. Okay? All right, so locally originated routes. So let's see here, step number 3. We prefer the path locally originated, which is the quad 0, using either a network or aggregate command. We could have paths that are sourced by the network statement, then paths that are sourced by redistribution, and then local paths sourced by aggregate address, which is summarization, and the network and redistribution are going to be preferred. Actually, there's a little bit more to this, and I'm going to add to that right now. We know that, I think I'm missing it actually here, locally originated routes have a weight of 32,768. I know it's in the section prior to that, in the weight section, but I want to make a note here again because that's the kind of route that we're talking about in this particular case. The locally originated routes, well, we talked about this actually. I was thinking about how I wanted to describe this, but we talked about this in our previous lesson, right? The different ways that we can originate network layer reachability information. The network statement is typically the first way, and that's how we're going to show. We're going to show those with an origin code of IGP, redistribution with an origin code of incomplete, and then conditional advertisements we talked about previously. So when we talk about this, there's really not a lot of decisions that are taking place here. Either the route is locally originated or it's not. I mean, it's a prefix that exists on my router, or it's a prefix I'm learning from other routers. But there are different ways that we can source those routes into BGP, right? We can source them with a network statement, we can source them with redistribution, or we can source them with some sort of summarization. And that's the order of operations there. Network would be preferred, redistribute would be preferred over finally the summarization option. Okay. All right. Next, we're going to look at AS path. AS path is really straightforward. The shorter length is preferred. This is really a common way to affect inbound traffic flows. Okay. So this is a, I should actually, well, I can't really identify this one as inbound or outbound because there's no designation here because either the route is on my router or it's not, right? I can't change that behavior. With AS path, though, I can change that behavior. I can either ignore it by simply doing a BGP best path, AS path ignore. I can also manipulate the AS path by doing some sort of AS path prepending, where I can actually incorporate additional hops, if you will, in the AS path. Now, this is considered to be, as we saw with these previous examples, these are inbound policies. AS path is an outbound policy. Actually, let me think about that a second. Could it be an inbound or outbound policy? It actually could be an inbound or outbound policy because we can apply prepending to the routes that we're learning from a peer, or we can prepend routes that we're sending to a peer. So this could either be applied as an inbound or outbound policy. All right. This is a common way of affecting inbound traffic flows, specifically by doing like to set some sort of prepending out option. If you look at the internet table and you see an AS listed multiple times, it means that they're doing some sort of prepending. They're adding additional ASs to the path. Okay. I'm trying to think if I should identify this primarily as an outbound policy or as an inbound policy, but I believe that we could manipulate that in either direction, right? I could say, okay, I could come to my topology here and say, okay, for anything that I'm learning from this peer, from this IP address, let's go ahead and prepend, 51 multiple times. And then anything that comes in this link, I'm not going to do any AS path prepending. Or I could conversely say any prefixes I'm advertising this peer, I could set the AS path and prepend 100 multiple times. And on this one, I could maybe not do it. So again, yeah, Ken, you're right. It does depend primarily on the perspective. But think about it again. It's not 6 of one, half a dozen of the other, because inbound policies only affect outbound flows, and outbound policies affect inbound flows. So depending on how you're applying it will depend on whether or not you're trying to influence how you decide to leave the autonomous system or how the other people decide to get to your autonomous system. Okay? All right. The next one is origin code. Let's go back to our diagram here, our text document. We prefer the lowest origin type. All right. So we're going to prefer IGP over EGP over incomplete. So there are some status codes that exist here. And let me actually put this in here because I didn't put this in last time. IGP is going to be greater than EGP, which is going to be greater than incomplete. So if I go back to my routing table here and I do a show IP BGP, we can see the origin code listed here, right? IGP, EGP versus incomplete. Now, realistically, you're probably never going to see this one, right? EGP literally means the routing protocol EGP, which was the very first routing protocol that existed. So you're either going to see IGP or incomplete. We don't see EGP too often. Not a whole lot to say about this particular policy. This would also not be described as an inbound or outbound policy because, either the route is coming from some sort of aggregate process or redistribution process, or it's coming from an internal peer. And that's the only way we can identify that. If I look at this output here, 7.7.7.7, that's showing that it's coming from an IGP. Let me go over to router 5. All right. So it's different in this case. This is the path that we're selecting to go to 75.7. That has to do with the manipulation that we did previously. Remember, that link is probably still shut down from our previous discussion. We were manipulating how paths, how traffic would flow here based on which link was active or not. I'm not going to get into that. We're not going to modify that right now because it doesn't really matter. And the reason it doesn't matter is because we're not going to actually be doing any manipulation. It's odd that they've never corrected that formatting issues. Has it always been that way? You're talking about the path column, Chris? What are you referring to specifically? Just generally how the table looks? Yeah. Yeah, it's interesting, how it's listed here, but it's correctly formatted, but it's just the way that you interpret it. We're going to take a look at, the origin codes. It's a little confusing, right? Because you've got internal up here with a little I, and then you've got IGP here with a little I. So are we talking about this is internal, or this is internal, or this is IGP, or this is IGP? Actually, we're actually kind of referencing that this is the IGP component, the origin code. So it is, you're right, it is a little bit strange how we see that, okay? Now, the reason why I was saying that we don't really classify this as an inbound or outbound policy is because we really can't change the behavior. right? Either depending on how the route is processed, how the route is learned will determine what kind of origin code it's going to have. Okay. Now this is definitely an outbound policy. So we have 2 outbound and 2 inbound essentially. AS path is typically going to be defined as outbound. I would actually even document that. This is typical for typically outbound. But again, it could be applied inbound. But MED is definitely an outbound policy. It's an optional non-transitive attribute. And it's probably one of the most confusing attributes that you're going to see. All right, it's called Multiexit Discriminator. And we're actually going to spend a lot of time talking about this particular attribute later on, because there's a lot of different ways to execute this and a lot of different ways about how this works. In general, the smaller number is going to be more preferred, but this is only going to work if you're peering to the same provider multiple times. And there are multiple exceptions here. So this is a optional non-transitive attribute. So if I go back to my diagram here, actually my snippet here, I would be advertising a MED to peer 7, to router 7, and then router 7 can then make a decision on how to route to router 5 based on that multi-exit discriminator value. So if I have a lower MED here and I have a higher MED here, router 7 could say, okay, I'm going to go ahead and route to you using that attribute, and because I prefer the lower number, because that's a value that you're sending me. Again, router 7 can completely ignore that. They don't have to follow that rule. Right? Generally, it's considered to be kind of best practice or at least common courtesy to if somebody is trying to tell you how you should route, you're going to go ahead and accept that, but that's not always the case. There are a lot of other exceptions to MED. Let's say, for example, router 7 is AT&T and I have 2 peerings. I'm going to advertise my routes to router 7. They're going to have the same AS path. In this particular case, they're going to have a lot of the same attributes. I want to affect my path selection inbound. I can tell router 7 to prefer one path over the other. Typically what the MED is normally it's an indication of the best IGP path, because the value itself actually reflects the metric for that IGP path. This is my best internal path to the destination. So when you do the network statement for IGP, for the IGP route, it's going to automatically copy the metric value into the MED value. That's why, by the way, when you see it listed in the BGP table, you don't see it listed as MED, you see it listed as metric. So this is actually the multi-exit discriminator value. There's the local preference, there's the weight, there's the AS path. So these are the primary attributes that we use to make a path selection process in BGP. The next hop is not really used it could be used, I suppose, potentially as a tiebreaker, but after we've gone through all the other processes. But the next hop is really, do I even make an attempt? Do I even make an attempt to go through the best path selection process based on the fact that I am, is this a best route or not? You know what I'm saying? So I don't know if I described that very well. The next hop needs to be recursable. We need to be able to reach the next hop before we can decide if we're going to look at metric, we'll look at AS path, look at weight, look at these other attributes. All right? All right. In most cases on the internet, the MED is not going to be used. Maybe with the exception of internet exchanges. It's really just too complicated to work with, and there are frankly just easier ways and better ways to influence path selection. So MED is not going to be a very common value. All right, let's see. Non-transitive, it's a suggestion sent from an EBG peer to another EBG peer to suggest how that neighbor is going to route. Lower number is better. We can manipulate this with route map, and the peer can choose to ignore that suggestion. Number 7, pretty basic. We're going to go ahead and prefer eBGP over iBGP. Now, we've talked about this a lot when we talked about administrative distance. But in this particular case, it doesn't really have anything to do with administrative distance. Even though eBGP routes do have a lower administrative distance than iBGP routes. If I'm learning a route from an external peer and I'm learning a route from the internal peer, I can pretty much guess that that particular route is not originating within my autonomous system. It's got to be originating from somewhere out. So I'm going to just try to find the closest eBGP path to the external neighbor as opposed to routing to the most optimal internal neighbor. And this is what we refer to as hot potato versus cold potato routing. All right. Then we might go with the lowest IGP metric to the next hop. That's where I was saying, now we're kind of getting into the tiebreakers a little bit. This is where I was saying where the IGP process or the next hop value might come into play. I can re-explain that, Ken. Ken mentioned that he was a little confused on that statement I made. All right. First of all, again, I'm talking about if I'm going to choose, let's say I learn about prefix 7. Here, let me go back to my diagram here. And let's say for some reason router 4 is learning about, well, actually in this case it would be the case. Actually, let me go to router 5. It'd be better to look at this from router 5's perspective. So router 5 is learning about the 7777 prefix. All right, and let's say we're not doing next hop manipulation, or we've got a route reflector in here. So the 777 prefix is being learned to router 1. Router 1 is sending it to router 4. Router 4 is then reflecting that to router 5 as an iBGP route. Okay, I'm going to choose the eBGP path over routing internally because that's my directly connected peer. And I'm not going to choose the iBGP path because that even though it may seem to be more optimal, it's not. I know that the prefix exists outside of my autonomous system. So I'm not going to route to another internal peer to reach that external network. All right. And Ken, you mentioned just because iBGP doesn't pass network layer reachability information to other iBGP. In this case, it would. And you're right, it doesn't unless you have a full mesh. But we would have to design our BGP AS with a full mesh anyway because we want to have that network layer reachability information. Let me go to router 5 real quick and check something. So you can see here in this case, I'm not getting. Let me check router 8 real quick. I think I left router 8 section BGP. I think I left router 8 unconfigured from the last time. Yeah, let's do this real quick. Router BGP 50, neighbor 172.16.18.1, remote AS 100, and neighbor 78. 172.16.78.7, remote AS 51. All right, so I'll let that converge here, but hopefully what I'll end up seeing is what I suspect I'd see, which is what router 4's decision is, show IP BGP. So router 4 still getting the information from router 5, but I should eventually see that information would come in from router 8 as well. Let's make sure router 8 is converged. So we're not getting, let me check router 7. I'm not sure. Yeah, I don't have it here. Config T, router BGP 51, neighbor 172.16. I keep forgetting what the 78 remote AS50. Oops. I meant to put this as .8. All right, now I should be seeing on router 8, 7 coming in multiple ways. Yeah, so we're learning about this prefix 7777 from the link going between router 7 and router 8, and the link to router 1. Now we're choosing this path simply because it has the lowest AS path. But we can see here the metric is specified here, but it's not specified here. But I want to go back to router 5 real quick. And router 5 is not where I want to be. I want to be on router 4. Remember, router 5 is only going to see whatever router 4 decides to use. And I should be getting from router 1 from router 1. I'm only getting it from router 3 and router 5. Router 4 should be learning this prefix from router 1 because router 1 should be learning it from router 8. Router 1 is learning it from router 8. Router 1 is choosing to go to router 7. So why isn't this being propagated? I get why it's using this path. That makes sense. We're going to go to router 7 because, or router 5 and then router 7. But what I'm trying to figure out is why router 4 is not seeing that other path. And it's probably directly related to what I was just talking about. We're going to prefer eBGP over iBGP, right? And router 4 would be learning that prefix from an iBGP peer. Yeah, I mean, Ken, you're right. The ultimate decision in this case, we haven't even gotten down to this point in the decision tree because AS path has already been decided. AS path is already deciding how we're going to make this route decision. I'll tell you what, I'm going to table that discussion for now because we are going to get into, let me save these configs. We are going to get into a discussion about how do we manipulate these values. How do we understand these values, and I'll probably get back into this decision process. Maybe I can come up with a scenario where we can simulate, finding that closest eBGP path to the external neighbor, as opposed to routing, over some sort of internal neighbor. I would recommend that you do a Google search, Ken, if you want to read more about this concept on hot potato versus cold potato routing. Specifically with BGP. It's not a BGP only concept, but if you just do BGP hot potato routing, there's probably some great documentation that describes this concept that I'm not describing very well to you, unfortunately, at this point. But this is one of those things that you might have to visually see as opposed to talk about. All right. In other words, if I'm learning about the path through multiple next hops, I'm essentially going to choose number 8 in this case. I'm going to choose the path that gets me to that next hop quicker. Okay. All right. If this value is equal, then we start doing something called multipathing. We're going to spend a lot of time talking about multipathing later on as well. There is a hidden command, BGP best path, AS-path, multipath-relax. We'll talk about this later when we talk about how multipath is different. It's definitely different in BGP versus some of the other protocols because there's a strict requirement that says that the AS path has to be the same length in order to do multipathing with BGP. So if I have equal routes to the edge routers, then I can actually do multipathing to both of them. All right. And that would be identified by the IGP metric to those edge routers. All right. And that's where multiple paths, we were saying multiple paths require multiple routes with BGP multipath. All right. Now at this point, I can even make a note in the list here. At this point, we are now down to the tiebreakers. All right. We typically would never get to this point in our decision tree. You could certainly manipulate some of these values to manipulate how path selection works, but quite frankly, it's a lot easier to do the manipulation with one of the other well-known attributes, or at least one of the other basic attributes that we're typically used to dealing with. All right, like weight or local preference, AS path, stuff like that. Okay. So what are the tiebreakers? Well, things like oldest route, which router has the lowest router ID, the shortest cluster list length if I'm a route reflector, the lowest neighbor address potentially, and so on. All right. Ken says here, gotta love the command that says relax. Yeah, that would definitely be a command that would be useful on the test. Hopefully you're not getting to that point though. All right. Like I said, most of this we don't really care about because if we're influencing path selection, we're always going to change the attributes to override anything in this behavior. We could change the router ID, just easier ways to do it, right? But, you know, you may get a question on the exam that says, you know, influence the routes based on a tiebreaker. Don't change the AS path. Don't change the med. Don't change the local preference. And you end up having to go to maybe setting a router ID or, you know, picking the oldest route or whatever. All right. They're not trying to do this necessarily with these values as far as influencing the route. Because at the end of the day, we can only select one best path. Even if we're doing multipathing, we can still only select one best path, and we can only advertise one path to our peers. All right? Now, one of the things I did not put in here that I did want to add to these notes here are what are the exceptions? Best path exceptions. And in a lot of cases, these would have to be configured in order for these exceptions to work, but I do want to kind of put in some of those commands. So we could do BGP best path, AS-path ignore. So in this case, we're overriding the AS path component of the selection process. With med, gosh, there are a ton of exceptions. All right, but we could do like a BGP always dash compare med. We'll talk about these a little bit later. This would be like comparing meds even if they come from different ASs. It'd still have to be on the same router, but we could have peering relationships with different peers. We could do the BGP best path med-confed. This would be related to med as well, obviously. This compares the med for routes that are locally originated in a confederation. Probably not, that probably didn't explain it. It's not really that important to understand at this point. Like I said, we're going to spend a lot of time talking more and more about med later on. Okay. We could compare the med. Say, for example, this would also compare the med between different confederation peers. Very similar to the idea of comparing it between different autonomous systems. All right. Now we also have with MED, BGP best path, MED missing as worst. Now this is also something that's a little bit confusing because we're talking about the MED attribute not being set at all, as opposed to a MED of 0 or a null MED. All right, so as opposed to assigning a MED of 0, I could assign a MED, let me put this in here, of 0 or an infinite MED. All right, so the default is null, which does equal, in this case, 0. But that's not equal to null infinite. All right. If I have a MED value that's assigned to null infinite, that's going to have a value of 4 billion, 294,967. Let me see. Let me Google this number real quick. I want to give you guys the right number. This is a pretty common number you see for infinite metrics. So if I usually search the number alone, yeah, it's 2 to the power of 32 minus 1. There's a specific reason why this number is used, but 295. All right. It would actually be 294 because you have to subtract 1. This would be a null MED infinite. And again, we'll talk more about the reason why we may want to do something like this, but it's kind of beyond the scope of what we're talking about today. Remember, there are many, many different things you can do with MED. Another one is BGP deterministic MED. Deterministic MED. I was always very thankful. I don't know if I spelled deterministic. Yeah. Always very thankful that MED is not one of those things that's used that often, because it's just really one of the most confusing attributes in BGP. All right. So this would say, let's go ahead and compare the MED. Let's compare the MED against all possible paths. And in addition, this changes the selection order in general. All right. A lot of these will come back in detail. They're very, very specific exceptions. There's another exception that doesn't have to relate to MED. It's the IGP metric option. And in this particular case, we can do a BGP best path, IGP metric ignore. And let me see if that's actually available in this BGP best path IGP metric. Yeah, ignore. So it is part of this iOS. You can see that there are a couple of different options: compare router ID, cost community, IGP metric, MED, and so on. But the best path IGP metric ignore, obviously, kind of makes sense what it means. That means that we're going to ignore the IGP metric. This was introduced in iOS XE. I think it was 3.4 something, but obviously it's been carried over into this iOS as well. Router ID, again, just like we saw with IGP metric, we can say no BGP best path, compare router ID. All right. So we have lots and lots of options.
The adjective right is usually defined as in accordance with what
happened. My Siri started talking to me. Router ID, and I think that's actually one of the options here as well. Yeah, compare router ID. Okay. So for identical eBGP paths, we can either select this as part of the process, or we can take it out. It's turned on by default. But again, you're not really going to get down to these tiebreakers because, frankly, these tiebreakers, yeah, Alexa hacked Siri. Yeah, I was thinking, yeah, it was, well, I named my Alexa computer, so when I say computer, she tries to talk to me, but all right. Okay, so like I said, you're not going to get down to these levels. I doubt you would ever get down to these levels when you're on the exam as well. It's not something you're typically going to see at the exam level because it's just way too much information, right, to be able to process and to be able to troubleshoot. But it doesn't hurt to know, right? So just keep in mind, checking the next hop reachability, that is not part of the best path selection process. It allows us to verify if the route is available before we go through the best path selection process. That's part of those pre-processing rules that we talked about previously. Now, how can we manipulate the best path? This is an important topic because the process of affecting outbound routing is completely different than the process of affecting inbound routing. You have ultimate control about how traffic leaves your AS, but you can only attempt to influence how traffic returns or enters into your AS. In most cases, like I said, there's kind of this gentleman's agreement, if you will, that says I'm supposed to really honor your attributes, but there's no real, actual rule or regulation that regulates that. So outbound policies affect inbound traffic flows, inbound policies affect outbound traffic flows. But keep in mind, before we get into any of those policy decisions, longest matched routing is ultimately going to trump everything, right? Because we're trying, I can't compare a 10.10.10/24 prefix to a 10.10.10/28 prefix. I'm always going to choose the 10.10.10/28 if the packet happens to match that particular prefix. And this affects routing in both directions. So if I really want to affect policy, because we deal a lot with aggregates in BGP, I could always leak out more specific routes. So if I have 2/24s or 2/25s, and I want to affect how routing works, I simply leak out a /26 or a /27. That's going to be the more preferred route, as long as the packet matches that route prefix. Okay. We also saw that we could kind of influence things with conditional route advertisements, where the best path selection process doesn't come into play, and that's another option. Okay. So attributes are going to allow us to define how traffic leaves the network. Those are my inbound attributes that allow me to identify my outbound flows. That's going to be local preference and weight. And for outbound traffic, that's going to be things like multi-exit discriminator and AS path. Okay. So based on our topology, if I pull up let me save this document here real quick. Where's my mouse? There it is. So again, based on our topology, we already kind of briefly looked at these examples. If I have multiple peer links to router 7 from router 5 in this case, there are multiple ways that the traffic can leave our autonomous system. We can also leave the autonomous system through router 3. I added that link from our previous exercise. So depending on the attribute that we're using, does it affect just the local router or does it affect everyone? Weight only affects the local router because it's a locally significant value, and it doesn't propagate through the autonomous system, which is why we, again, don't really use it, right? Local preference gets propagated through the autonomous system. That means everyone is making the same decision based on the path selection process. And the default local preference value is a 100. So let's say we want traffic to leave router 3. There's two ways I can do that. I can come into the router. Let me go back to my diagram here. We're talking specifically about local preference. And I could set the local preference to be higher for routes that I receive from router 7. So I could come in here and I could say, let's set the local preference to 200. Or I could do the opposite of that, right? I could maybe depress or poison local preference values on a different path or in a, from a different peer to make those less preferred. So I could say, let's go ahead and leave router 3 to default, and let's set the local preference to the routes that I'm getting on from router 7 here to 50. So I'm poisoning essentially the local preference value, which negates the best path, and then the other path will be selected. Okay. Keep in mind also, because we do have a route reflector here, we don't have a full mesh. We're only going to know router 4 is the route reflector. So router 3, router 1, router 2, they're only going to know the prefixes that the route reflector is selecting as the best path. All right. So that's something to keep in mind as well. Okay. Attributes that affect inbound path selection from the external peer's perspective are AS path prepending or setting the med value out. That means to say that I want to say, hey, when traffic returns, I want it to come back to router 5. So I need to change my outbound policy. But, again, that's not something that the other routers have to completely agree with. In general, you also have to take into account every ingress and egress path. Because if you're doing some sort of manipulation on one router and you're not doing it on another router, you could start to see some strange behavior as to how we're actually routing, because not everybody's seeing essentially the same thing. So if we're using AS path prepending, I could do something like prepending my AS multiple times on the path. I don't prefer, but it depends, right? When I look at an outbound policy, there's no way for me to check whether the overall result of that outbound policy was successful locally. I have to look at it from the perspective of external peers. So let's wrap up our lesson today by taking a look at that real quick. I'm going to go to routeviews.org. I don't know if all of this will work. I didn't try this ahead of time, but let's go ahead and connect to routeviews.org. No, that didn't work. Let me see if I got the right prefix. Let me go back here. Route views. There's one thing you can look at, routeviews.org. Maybe it's just supposed to be Telnet. Try Telnet. That's strange. There is I want to mention this anyway. This concept of the BGP looking glass, and there's many different references to this. The BGP looking glass is essentially a comprehensive list of all of the BGP route servers that exist on the internet. And I don't know why routeviews.org is not responding. I'm probably not putting it in correctly, but let's see. Those are the ones over at Oregon State. And I want to use that particular one. Let me just do this. University of Oregon, I think it is, actually. I think it's University of Oregon. University of Oregon BGP looking glass. I'm not sure why it's not resolving. Oh, it's route-views. So I can't just go to the domain. I just saw it, I think, listed here. Routeviews.org. All right, let's try that again. All right. Sorry about that. If we go ahead and log in. All right, let me change the font here so you guys don't go blind looking at this. All right. So anyway, if you Google BGP Looking Glass project, you can find a whole list of everything, but this is the one I typically look at. So if I go in here and I do a show IP BGP, and we're looking at just say the first example, the first prefix here, we can see that we're choosing 202.232.0.2. Now, I don't necessarily know how this router is choosing it. There's no easy way for me to say, hey, tell me why you chose that path. What I would have to do is kind of analyze it, show IP BGP 1.0.0.0. I would have to analyze it and say, okay, which path is the best path based on what value and so on, right? There's 31 possible paths available in this particular case, and number 28 happens to be the best path. All right, like I said, there's really no good way to ask BGP, how did you make the decision? You have to go look at the values, all right? And in our case, it was, let me go back to here. Oops. It was the 202.232.0.2. 202. And let me see, /202. Let me do that again. Show IP BGP. I don't want to have to scroll through all of them, so let's do 202.232 /202.232. And that should be it. Yeah. So we're seeing a local preference of 100. This is the best route. We could have searched for best as well. But we're not really seeing much else here, right? We're not, the AS path is kind of cut off because that was listed ahead of that. But in any event, I can't really tell necessarily from here how that path was selected. So it's not an easy thing to do. It's difficult, but you know, most likely this is going to be chosen based on our standard selection process. So let's go back to our BGP table and we look at the values here. So this has pretty short AS path. You know, as we're going through kind of eliminating some of the choices, it looks like weight is all 0, so we're not using weight in this particular router to make a decision. In some cases, the metric or the med is 0. We know that BGP med missing is not configured here, because if BGP med missing was configured, we would see that 4 billion number as opposed to just the blank, which is null, right? And so what we would do maybe to figure out you know, how this path is selected, we would go ahead and eliminate the longer AS paths and so on. There are some ways we could filter this database. We could use regular expressions. I know I've mentioned regular expressions a couple of times, but one of the things that I wanted to show you, because you may want to review this document as well, is Cisco terminal regular expressions. Because this document is not part of, it's not part of the BGP configuration document. Regular expressions are listed actually under terminal service configuration guides because they were used to search through patterns specifically used by terminal services and analog modem chat scripts. So you're not going to see this kind of in a regular BGP document. And I forget where it is. I think it's in the appendix, but let me see if I can find chapter regular expressions. Why is it blank? Let me go to configuration guides and then go to terminal services. Terminal Services Configuration Guide. I don't know why it's so big. And I think it's in the appendix. They might have moved it. I haven't looked at this in a while. Oh, there it is, regular expressions. Okay. But it's blank. Oh, that's crazy. Let me try this a different way. It's actually not easy to find. Let me try an older document here. I don't know why it's not popping up. Anyway, that's what you would Google, but I don't know that you need, I think I saw one pop up that said cheat sheet. Yeah, there's an INE document. I don't know that that it's something that you necessarily need to know, but it could be kind of useful, right? I'll give you a couple of examples here. So it's all part of that legacy terminal configuration. But the idea is that we're going to be able to search through patterns, but specifically with BGP, Mike says here, there is a Cisco regular expression reference, like a reference document. Yeah, most likely there is. I just couldn't find it. But if you want to post a link, Mike, I'll pull it up. But it's not really critical. Oh, there it is, right there. Let's see what this says here. So this is Mars. This relates to Mars. And it may not be the same with command line. That's the other thing about regular expressions, is that a lot of the characters that they use to describe different patterns are common between the different definitions of regular expressions, but they do vary from you know, like for example, here's an example, when you're doing wildcard matching in Call Manager, it's different than if you're doing wildcard matching in an iOS router. It's not quite regular expressions, but we do use regular expressions in voice over IP as well. For the most part, they're going to be the same, right? But there is some variation. And my point is, I guess, that the terminal services configuration guide is under terminal services. Those are the regular expressions that we're using for BGP. The other key thing to remember about regular expressions with BGP is that we're only searching on match conditions for a very specific thing, which is the AS path. We're not searching for other components within the AS path. So let's say I wanted to find all the prefixes in this route server that we only have one AS path. I would do a show IP BGP, for example. We're going to say it starts with a number, 0 through 9. And that's going to be repeated any number of times. And then we're going to terminate that with the $sign or the string character. It's not. Oh, I forgot my keyword regex. The other thing that you might see eventually, depending on the route server you're connected to, is that they're not going to let you run certain expressions because it can actually crash the router. So here's an example where I'm saying, okay, I'm just going to pull out all of the directly originated routes for my connected peers, right? And we can see the autonomous system numbers there. So it's basically someone who's originating a particular prefix. I can also say, let me see anybody who's originating from, originating a particular prefix. Regular expression, underscore, let's try 701. I think that's Verizon, if I'm not mistaken. And then we can see, all the prefixes that are being originated by Verizon, which used to be UUNet. All right, so there's ways to parse this information to look for what specifically it is you're looking for. And again, it's not something that you would necessarily need to know, but we were talking about AS path prepending, and I could scroll through and I could look through here and see, do I see any AS path prepending? I can see an example of it here. Is there another example? I could maybe possibly see other examples, but there's other ways to search for this. Let's say, for example, I did a show IP BGP regular expression underscore 7018 underscore 7018 underscore, right? So I'm looking for specifically any of these prefixes that have 7018 listed more than once. It's not responding very well right now because, again, we're parsing a pretty large database here, but we should see, I think I crashed it. We should see that output. Let's close that one. Let's see, yeah, there we go. So we're seeing AS path prepending here, 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 here. All right, we don't know what they're doing it for. We don't know what the purpose is, but again, we're able to filter. And you can see that none of these paths represent the best path for these destinations. This prefix specifically, we're learning about this prefix from multiple sources, and none of these are the best path. All right? So there's all kinds of ways that you can kind of filter out the information. I don't think, honestly, that any of these ways would be beneficial for you guys for the lab, because simply remembering all the expressions is probably a waste of resources, mental resources, if you would. Okay. We'll talk about multipath load balancing as well. We're going to get into that in a lot more detail later on. With multipath load balancing, it's going to work a lot differently, even from an internal versus external perspective. We still can only route with one to the best path, even if I have multiple routes that go into the rib and into the fib, and so on. And this is going to be enabled for IPv4, IPv6, VPN-v4, VRF-AF. We can do it for iBGP, we can do it for eBGP, we can do it for EIBGP, which means we're implementing it for both. But in general, we don't get to the multipath decision process. We're focused primarily on weight, local preference, AS path, and MED. All right, so that concludes our lesson for tonight. Hopefully we able to give you guys some additional information that you didn't have previously, and just, you know, looking at it again, it can be pretty helpful. So we will take a break for the weekend. You guys can enjoy your holiday weekend. Go back and review. I'm going to go ahead and upload this video right now. And I've got my Google Drive synchronization turned on, so it should upload. And we'll most likely do a Monday session and a Tuesday session. But we'll coordinate that this weekend with the Slack messages, okay? Any questions before we wrap it up? Alrighty. Monday is Labor Day. Yes, we are not going to have a session on Monday. A session on Tuesday. That would probably most likely be our first session, Tuesday. All right. So thanks a lot, guys. I'm going to wrap up this video. We'll see you guys in the next lesson.